Gallatin Range, Montana Territory, January 1866. Midnight. Outside, the valley lay locked under 6 feet of snow, the kind of high mountain cold that doesn't just sting your skin, it chews on your bones. The wind came screaming down the draw at 30 miles an hour, driving powder against cabin walls so hard it sounded like sandblasting. The thermometer nailed to the post outside the trading shack read 20 degrees Fahrenheit and falling. This was the night the cabins were supposed to fail. Standard log cabins in these mountains leaked heat like sieves. Single wall, hand-hewn logs, moss and mud in the gaps if you were lucky, rags and old flour sacks if you weren't. Families had packed their walls with anything they could find: dried grass, horsehair, sawdust, even shredded newspaper. More mass, more material, more insulation. That was the rule. You know that rule. You've been taught the same idea in modern terms. But at the far edge of the clearing stood one cabin that broke it on purpose. From the outside it looked wrong. Taller than the others, eaves pushed out, windows set deep like the eyes of a wary animal. Under the snow-loaded roof, the walls were thicker, too thick for a poor homesteader. And inside those walls, where everyone else had stuffed wool and scrap and anything to slow the cold, this man had left air. Not empty, just mostly hollow. The owner was Elias Brandt, a wiry, dark-bearded mountain man who'd trapped these ridges before most of his neighbors could find them on a map. 2 winters earlier, he'd nearly lost 3 toes in a standard cabin when the indoor water barrel froze solid 3 feet from the stove. That night, wrapped in every blanket he owned, he'd stared at the log wall and decided he would never trust normal construction again. All that summer, while his neighbors felled trees and bragged about how tight they would chink their cabins, Elias built something different. He raised 2 wooden shells with a gap between them, a double wall with an 18-inch cavity running almost the full height. When asked what he'd fill it with, he'd said one word: air. They laughed in his face. "Can't heat nothing," Samuel Creek snorted, spitting tobacco in the dust. "You want warm, you pack those walls till they bulge." William Thorpe, the most respected builder in the valley, shook his head. "You'll be burning wood till June if you live that long." To them, a wall full of air was a wall full of failure. But on this January night, their confidence was frosting over. Literally. Inside Samuel's cabin, a thin sheet of ice crept down the log seams, tracing every draft line like a map of mistakes. His children slept in their coats, breath hanging in the air as a pale fog. The iron stove, fed since dusk, glowed dull red, yet the room hovered barely above freezing. At William's place, a wet wool smell clung to everything as they huddled around a sputtering fire, hands aching from hauling in the last of the split pine. Their cabins were built right. Their families were still shivering. Now, let's see what Jacob built. Not yet. First, you need to see what Elias's wrong cabin was doing. Across the clearing, his air wall cabin leaked lamplight at the edges of the curtains, a soft, steady glow against the snow. No roaring chimney, no frantic parade of wood from the pile. Inside, the air held a quiet, even warmth, the kind that seeps into your fingers and lets your shoulders finally drop. Frost traced the outside of his outer wall and stopped there, as if the cold had hit a barrier it couldn't quite explain. What did this stubborn mountain man understand about heat and air that 2 generations of frontier builders and most modern homeowners had missed? Before we reveal the exact technique, hold this picture in your mind. Neighbors, wrapped in blankets, inside cabins packed with insulation, while the man who left his walls mostly hollow sat reading by lamplight, sleeves rolled up, in a winter where the difference between survival and catastrophe could be measured in just a few degrees. Elias Brandt's air-filled walls were breaking one of home building's biggest rules. And if he was right, his lonely cabin in a forgotten Montana valley is holding knowledge that's been buried for over a century. Knowledge that still has the power to embarrass modern insulation thinking. So what did this stubborn mountain man understand that everyone around him was missing? Not about fire. They all knew how to burn wood. About air. He was betting his life on something his neighbors treated as a nuisance. To them, air in a wall meant drafts, squeaks, and that knife of cold you feel on your neck at 3 a.m. To Elias, still air, trapped and tamed, was the only insulation he could afford to haul into the mountains. And that brutal winter turned his cabin into a real-world experiment no university would dare to run. Same valley, same wind screaming off the ridges, same piles of frozen lodgepole stacked by the door. The only variable was the wall. His neighbors had the classic frontier cabin, single log shell, chinked with mud and moss, maybe a rough board lining if they were ambitious. Elias had a double shell with a gap of almost nothing in between. They all started winter with the same smug confidence. By late December, the numbers were humiliating. Inside the standard cabins, with the fire dying down, thermometers sagged into the high 30s. On good nights, maybe 42 degrees Fahrenheit if you kept feeding the stove until your eyes burned. Frost on the inside of the wall. Boots freezing solid by morning. And those cabins were chewing through 2.4 to 2.8 cords of wood every week. Evenings sat at 64 to 68 degrees Fahrenheit. You could work in a shirt with your sleeves rolled. By dawn, with the fire long out, his main room was still in the mid-50s, 20-plus degrees warmer than his neighbors, on roughly half the wood, about 1.2 cords a week. That's not magic. That's physics. Conduction, convection, radiation. 3 enemies, all fighting through a wall that looked wrong to frontier wisdom. The logs wanted to conduct heat straight out into the cold. The air wanted to rise and fall in lazy loops, carrying warmth away. Every glowing surface in that cabin wanted to radiate its heat straight through to the night sky. But a narrow, sealed air cavity changes the rules. Still air has real resistance to heat flow, about R1 per inch if you don't give it room to start circulating. Elias's wall used that thin gap like a brake pedal on all 3 modes of heat loss. The inner shell warmed the air. The trapped air slowed conduction. The outer shell blocked the wind and cut radiation to the frozen world outside. Before we reveal the exact technique, look at the question this raises for you. How did a man with no textbooks build a cabin where the insulation was mostly nothing and end up more warm and less hungry for firewood than people following the rule book? Now, let's see what Jacob built in our earlier story. Stone as thermal battery, air as gasket, wood as shell. Elias was playing a parallel game with different pieces. Both were tapping knowledge that's been buried for over a century. How to make conduction, convection, and radiation work for you instead of against you. In the next part, we'll open up Elias's wall layer by layer, show you exactly how wide that gap was, how he controlled air movement, and what modern builders and DIY cabin owners can steal from his design, even in a world flooded with insulation marketing that loves to ignore the power of plain, trapped air. But hold up. Before we reveal the exact technique, freeze this moment for a second. Outside Elias's cabin, the wind is still throwing itself against the logs. Snow is scraping sideways across the mountains. That kind of high plains winter cold that finds every gap, every nail hole, every careless crack in a wall, and turns it into a tiny freezer vent. And right here, at this door, just a few inches of wood away, is air, supposedly doing the job of thick, expensive insulation. Now, let's not open it yet. Instead, I want to pull you into this with him. If you're still watching, hit like so this doesn't disappear into the algorithm snowdrift, and subscribe if you care about cabins and real heat, not just brochure promises. Drop a comment with where you're watching from. Are you in Phoenix heat, Minnesota cold, a damp UK winter, or a little off-grid place in the mountains? Because what you're about to see with Elias's empty wall matters in all of those climates. Still air has an R value of roughly R1 per inch if you keep it from moving. If you let it spin in big cavities, convection turns that air into a conveyor belt for heat loss. What did this stubborn mountain man understand that the sales flyers rarely explain? He knew the difference between wild air and controlled air. In a minute, when we step through this door, we're going to measure it, exact numbers. Wall thickness from inner plank to outer log, cavity width to the half-inch. How he broke that gap up so air couldn't just loop from warm side to cold side all night. How those choices turned nothing into an effective R value that his neighbors with store-bought bats would have killed for. And here's where it gets a little uncomfortable. Modern insulation companies do not lead with, you can do a lot with careful framing and plain air. They lead with product, with foam, with fiberglass, with panels and membranes. Useful tools, absolutely. But there is knowledge that's been buried for over a century about what a simple, well-designed air cavity can do when it's paired with solid thermal mass. Remember, this isn't a fairy tale about a magic cabin. This is a story about thermal mass, air control, and frontier problem solving. The difference between survival and catastrophe in a winter like Elias faced. So as we stand at this threshold, think about your own walls, your cabin, your van build, that tiny home you're sketching on napkins. What if changing the size of a gap, the way you break up a cavity, the way you let stone or wood absorb and release heat, could shift your space from always cold to quietly, reliably warm? Now, let's see what Elias built. The door thuds shut behind him. Outside, the mountains are all teeth and wind. Snow grains hiss past the chinks, a low roar pressing at the logs. Inside, it's like someone turned the world down 3 notches. The howl becomes a muffled hush. The air is still. You can almost hear the cabin thinking, this is not an accident. This is not just a cabin. Now, let's see what Elias built. Where most men in that valley threw up 4 walls and called it good, Elias was doing something stranger. He wasn't just hiding from winter. He was waging a quiet war on it. On conduction, on convection, on radiation. He would never have used those words, but watch where his hands went and you see the strategy. He built double walls, notched inner logs, notched outer logs, an intentional gap between them, too narrow to crawl through, too wide to ignore. Neighbors rode by all summer, reining in their horses, squinting at what looked like a cabin inside a cabin. You building a barn around your house, Elias? They laughed at the wasted space. He kept setting boards like he was loading a rifle, because to him, every board was a shield. Every gap was a controlled battlefield. Frontier builders feared empty cavities. They stuffed them with moss, hay, whatever they could find, chasing the idea that more material meant more warmth. Elias did the opposite. He carved out nothing, long continuous chambers of still air. Here's where the physics hides in plain sight. Heat in winter tries 3 tricks. It conducts through solid wood, it rides tiny air currents, it radiates like light from a lantern. What did this stubborn mountain man understand, without equations, that others missed? That still air trapped and divided can be armor. An inch of air, sealed so it can't swirl, is roughly R1. Stack inches, break up the loops, and suddenly nothing slows the cold. So while neighbors packed their single walls tight and watched frost creep across interior boards, Elias was fighting a different enemy: movement. He broke the cavity into smaller cells, horizontal nailers, occasional diagonal braces, each one chopping up potential convective loops before they could form a conveyor belt of cold from outside to in. From the road, it looked foolish. Extra logs, extra labor, no stone, no eye, no visible insulation, just air in a Montana winter. But step inside on a night when the mercury knifed down toward minus 20 degrees Fahrenheit, and the contrast was brutal. Their cabins hovered just above freezing, breath smoking in the dim light. His stayed quietly, stubbornly warm, the fire idling instead of raging. On the frontier, survival favored clever over conventional. This wasn't tradition. This was a man choosing physics over habit, whether he knew the word or not. And the most radical part of his wall wasn't what he added, it was what he left out. Before we reveal the exact technique he used to make nothing into insulation, you need to see how far he pushed this air fortress and what happened when that first real test storm settled in for 3 relentless days. The first thing to understand is what Jacob was up against. Most cabins in those mountains were single-wall boxes thrown together between the last thaw and the first real snow. Logs notched and stacked in a hurry, a smear of mud, moss, or horsehair jammed into the cracks, maybe a layer of rough planks inside if the family had extra boards. One wall, one skin, one thin line between a glowing stove and a 20 degrees Fahrenheit night. Heat came from a corner iron stove or a rough stone fireplace that smoked as much as it warmed. You can picture it: orange fire, black pipe, a ring of boots and blankets pulled in close. Step 2 feet back from that circle, and the temperature dropped like a cliff. The cabin never really felt warm. The stove just carved out a temporary bubble of survival. Those single walls leaked. You could feel the winter sneaking in. A fingertip held near the chinking found little knives of air sliding through the gaps. At dawn, the inside of the one small window would be filmed with ice, lace patterns of frozen breath, and cooking steam. If you pressed your hand to a log, it felt dead cold, like touching stone in a root cellar. The wall was busy conducting heat straight out into the dark. Neighbors didn't talk about conduction or convection. They talked about bad drafts and the cold getting in. But the physics were merciless. Warm air inside pressed into every crack, leaked out, and dragged new cold air in behind it. The walls themselves, 8 or 10 inches of solid wood, were just bridges for heat to walk across. Radiant heat from the stove beamed to the logs, then bled away to the night sky. How fast did that happen? On a clear January night, at 10 degrees Fahrenheit, a well-fired cabin might hit 60 degrees Fahrenheit near the stove by 9 in the evening. Let the last load of firewood burn down, and by midnight, you were at 45 degrees Fahrenheit. By 2 in the morning, 38 degrees Fahrenheit. That's a 20-degree plunge in about 2 hours once the real coals died. Water buckets skimmed with ice. Bread dough froze. Breath smoked in the air inside the cabin. This was normal. This was frontier life. Families slept in layers of wool, caps on, children bundled 2 to a bed, not because the cabin was badly built by their standards, but because no one expected a cabin to hold heat. You woke to frozen boots and a crust of ice on the wash basin, and you were grateful the roof hadn't blown off. What did this stubborn mountain man understand that his neighbors didn't? He saw that those cabins were fighting 3 enemies at once, heat conducting through solid wood, uncontrolled air currents sneaking through every gap, and radiant losses to the endless black above the mountains. Knowledge that's been buried for over a century was hiding in plain sight. If you could slow all 3, you could change the difference between survival and catastrophe. Before we reveal the exact technique he used, you need to see how he turned the one thing every cabin already had, air, into a weapon against that cold. So let's pull the walls apart for a moment and watch how the heat actually escapes. Not in theory. In your cabin, in a Montana winter, when that fire is the only thing between your fingers and frostbite. First, conduction. Think of it as heat sliding through solid material, hand to hand, log to log. The inside face of a wall gets warm, the wood fibers start to vibrate faster, and they pass that energy along toward the cold side. Give it a few hours, and that once cozy interior wall is chilling down because it's been quietly feeding the exterior surface, which is bleeding into the night air. Standard single-wall cabins made this easy. 1 layer of logs, maybe 6 to 8 inches thick, chinked with mud that froze and cracked. The temperature difference between inside and outside in those mountains could be 80 degrees. Conduction loves that. The bigger the difference, the harder it drives, until your beautiful log wall becomes a giant wooden slide for heat to rush out on. Then there's convection. This is heat hitching a ride on moving air. Warm air rises, cold air sinks, and if you give that air a path, it will carry your heat away like a thief with a sack over his shoulder. Every gap in a wall, every poorly sealed ceiling joint becomes an invisible chimney. Warm air sneaks up and out, cold air pours in low to replace it, and you're stuck feeding the stove just to fight a current you can't see. Frontier cabins were full of these hidden chimneys. A knothole here, a loose board there, a gap where the roof met the wall. The neighbors called it good ventilation. In January, with a north wind at 20 miles an hour, that ventilation was a conveyor belt shipping heat straight into the sky. Third, radiant heat. This is your body, your iron stove, wildly shining energy out in all directions. You feel it when you stand in front of the fire, and your face warms while the air is still cold. That radiant warmth flies in straight lines until it hits something colder, a window pane, a log, the underside of a snow-loaded roof. Those surfaces can reflect a little, but most of the time they just absorb it and then leak it to the outdoors. Put all 3 together in a typical frontier cabin, and the picture gets ugly. Conduction hauling heat through solid wood into sub-zero air. Convection pumping warm air out through cracks and hauling cold air in at floor level. Radiation beaming your hard-earned warmth toward frozen walls and a black winter sky. In a 20 degrees Fahrenheit wind, every square foot of wall was working against the people inside. What did this stubborn mountain man understand that his neighbors did not? That you can't stop heat from trying to escape, but you can slow each path dramatically. Conduction hates long, broken routes. Convection dies in small, sealed pockets where air can't loop. Radiant losses shrink when warm surfaces don't see the cold directly. And this is where air, carefully trapped, stops being a weakness and becomes a weapon. Still, air has real resistance to heat, flow roughly R1 per inch when you prevent those little convective swirls. Turn a single big, drafty cavity into many tight, controlled spaces, and suddenly conduction has farther to travel, convection has nowhere to go, and radiation hits warmer interior surfaces instead of the brutal exterior cold. Before we reveal the exact technique Jacob used, you need to see how he reshaped that invisible battlefield inside his walls. Now, let's see what Jacob built when he decided to make the air itself fight for him. Out on that frontier, air had a reputation. It was the enemy. If you woke up with ice on your blanket and a frozen water bucket beside the bed, you didn't blame thin walls or poor design. You blamed the wind getting in. This was the frontier mindset. Cold meant drafts. Drafts meant gaps. So every cabin builder from the Missouri to the mountains went to war against the tiniest sliver of daylight between logs. Moss hammered into seams, rags wedged into corners, mud smeared into every joint until the wall looked more like rough masonry than timber. If you could press it into a crack, they used it, all with one goal: drive the air out. They didn't just fear moving air, they feared air itself. Early builders never separated the idea of a screaming draft under the door from the idea of still, trapped air inside a wall. To them, it was all the same invisible thief, carrying heat straight into the teeth of a Montana winter. If your cabin was cold, clearly there was too much air in the walls. So they built accordingly. Single log walls, packed and chinked until no light showed. Later, when board walls and framed cabins appeared, the instinct stayed the same. Fill every cavity completely. Straw, sawdust, shredded bark, even dried manure in some desperate homesteads. Anything low density they could cram between boards to get rid of the air that, in their minds, was leaking the heat away. What did this stubborn mountain man understand that his neighbors didn't? He knew there was a difference between wild air and captured air, between a roaring draft under the sill and a thin, sealed pocket of stillness that barely moved at all. One strips heat off your skin in seconds. The other slows conduction, chokes off convection, and quietly works as insulation. But on the ridge, that idea sounded insane. When Jacob mentioned leaving cavities, neighbors shook their heads. You leave empty space in that wall, you'll freeze solid by Christmas. To them, an unfilled gap wasn't a design choice. It was negligence. Even today, you see the same instinct. DIY builders with a new framed cabin, shoving bats into every stud bay, compressing them until they bulge, convinced that if there's any visible void, heat will pour through it like water through a hole. Here's the twist. The more they crammed, the more they sometimes sabotaged their own cabins, creating hidden paths for convection or wet, compacted insulation that barely slowed the cold. They were fighting the wrong air. They tried to eliminate every pocket when they should have been shaping it, sizing it, sealing it. Because what if the very thing they were trying to purge from their walls was the missing ingredient? What if controlled, still air, held in the right way, could have made those early cabins dramatically warmer with less wood, less labor, and fewer frozen nights? That's exactly the rule Jacob was about to break. And when you see where he put the air in his walls and what he paired it with, you'll understand why his cabin felt like a different world the first night the temperature plunged. So, one afternoon, with the wind already testing the gaps in every cabin on that ridge, Jacob cleared a space on his rough-hewn table and drew the thing that would make him a legend, a wall that was mostly nothing. Not thicker logs, not more stone, 2 walls with a deliberate emptiness between them. Now, let's see what Jacob built. On the outside, he sketched a standard log wall about 8 inches thick, notched and locked against the Montana winds. Inside, a second wall, again 8 inches. This one meant to stay warmer, drier, closer to the fire. Between them, and 1/8-inch cavity running unbroken around the entire cabin, from the stone foundation up to about 7 feet, like a hollow belt of air circling the room. To his neighbors, peering over his shoulder, it looked insane. Twice the logs, twice the notching, twice the labor in a short mountain summer, and then he was leaving the middle empty. In a world where every board had to be felled, hauled, and hewn by hand, that gap looked like pure waste. You can almost hear it. Reinhardt, you building a cabin or a flute? But Jacob wasn't drawing a hole. He was drawing a material. Air, treated like something you could shape, limit, and trap. While everyone else cursed the drafts that stole their heat each winter, he was thinking, what if the same air, held almost perfectly still, could become a shield against the cold? Here's where the geometry mattered. 18 inches is too wide to leave wild. A big empty chase lets warm air race up, cold air fall down. A convective loop that pumps heat right out through the wall. Jacob narrowed and controlled that space with cross ties in stone, breaking the cavity into tall, slow channels instead of one big chimney. What did this stubborn mountain man understand that his neighbors missed? That still air can reach around R1 per inch, but only if you stop it from rolling. He also paid attention to the faces of those walls. The inner log surface, warmed by the fire and by the stone mass he would later add, radiated heat into the gap. The cooler outer wall saw less of that radiation because the geometry and surface texture disrupted direct line of sight. Less radiant loss, less convective loss, conductive heat slowed by distance and wood. Before we reveal the exact technique he used to tune that gap with stone and framing, hold this picture in your mind. A cabin ringed by a continuous invisible blanket of controlled air. In a winter where a 20-degree difference inside could mean the difference between survival and catastrophe, that nothing in the middle was about to matter more than any extra log his neighbors ever stacked. That nothing in the middle only works if you understand one quiet number, R value. R value is just stubbornness. It's how unwilling a material is to let heat walk through it. A higher number means more resistance, more delay, more time before the cold outside the cabin bullies its way in. Under perfect laboratory-style conditions, still air comes in at roughly R1 per inch, which sounds pathetic until you realize what this stubborn mountain man understood. You don't buy that R value in bales, you shape it. Here's the catch. The word that matters is still. Air itself doesn't conduct much heat. The real danger is when it starts to move. The moment air in a cavity begins to circulate, it stops acting like a blanket and starts acting like a conveyor belt. Warm air rises along the inner wall, cools along the outer wall, drops and loops. That loop quietly hauls heat from the warm side to the cold side. No draft on your face, but your heat is leaving. That's why giant open wall cavities are a trap. They look like insulation, but in a hard Montana winter, they turn into slow motion pumps, churning precious warmth out of the cabin, especially when the temperature difference between inside and outside stretches to 40 degrees or more. The bigger the uninterrupted gap, the stronger those convective loops become. Now, pattern interrupt. If big gaps are bad, why didn't Jacob just cram the space with moss like his neighbors and call it a day? Because he wasn't chasing more material, he was chasing control. Now, let's see what Jacob built. His double log wall left a nominal 1/8 inch space, but in practice it wasn't one huge void. Stone courses, cross ties, and the irregular faces of the logs broke that cavity into a maze of smaller pockets. Each pocket was shallow enough that warm air couldn't get a good run at rising, turning, and falling. The result was layers of mostly still air, each one hovering near that ideal R, 1 per inch, wrapped around thousands of pounds of stone. Think about that. Instead of one big convective engine, he created a stack of quiet, reluctant layers. Heat from the cabin side moved by slow conduction into the stone, then bled, even more slowly, across those fractured air pockets toward the outer wall. Every broken path, every interrupted loop, bought him time. Time at 64, 68 degrees Fahrenheit inside, while the mountain sat at 20 degrees Fahrenheit. Modern builders do this without thinking about it. Double pane windows? That sealed gap between the panes is just a carefully sized air cavity, tuned so convection inside never really takes off. Insulated panels and some double stud walls rely on the same principle. Break the space, calm the air, stretch the path heat has to walk. Before we reveal the exact technique he used to tune that stone and air sandwich, remember this. In that winter, managing invisible air was the difference between survival and catastrophe, and it was built right into his walls. Now, let's see what Jacob built when that invisible air had to be wrapped in something that could take a Montana winter head on. From the ground up, his outer shell was pure frontier logic. No fancy milled lumber, no brick. He used what the mountains gave him. Hand-peeled lodgepole pine logs, stacked and notched, riding on a belt of stone. The logs shed water and wind. The stone kept the whole experiment from sinking into the thawing spring mud. The foundation came first, and it was not the shallow trench his neighbors dug for their cabins. Jacob cut down to hardpan, 24 to 30 inches in most spots, wide enough to spread the load of 2 walls and 8,000 pounds of stone. On that trench he laid fieldstone footings nearly 2 feet across, dry stacked but carefully keyed, then capped them with flatter stones to receive the first sill logs. Overbuilt? To his neighbors, absolutely. To Jacob, it was insurance. Remember, this was a double wall system, twice the wood, plus the stone, plus that 1/8-inch air gap. A normal cabin could skate by on undersized piers. Jacob couldn't. If the foundation shifted, the air cavity would pinch or open, and his carefully trapped air would start to move, turning from insulation into a conveyor belt for heat loss. On top of those footings, he raised the outer wall first. Log courses about 8 inches in diameter, saddle notched at the corners, so each timber locked the next one in place. Corners were his weak point if he got them wrong, so he overcut the notches, then drove hardwood pegs down through every third course. That let the outer wall stand on its own, a rigid box, while the inner log wall and stone core lagged behind in the schedule. Between each course, he chinked tight with moss, clay, and lime where he could get it, not to insulate, but to stop wind from whistling through. This shell was a shield, not a blanket. What did the stubborn mountain man understand that his neighbors missed? You can't let the wind touch your insulation and still call it insulation. Weather was the real enemy, so he pushed his eaves out farther than was common, 18 to 20 inches of overhang, enough that melting snow and driving rain broke and fell clear of the walls. He ran the logs so they projected past the corners, then trimmed crude drip noses with his axe, forcing water to drip off before it could crawl back along the grain. Siding orientation mattered too. Where he added rough sawnboards on the most exposed west wall, he ran them vertically, lapping each joint so water had to fight uphill to get in. Over doors in the single small window, he carved simple wooden drip caps, a primitive flashing that threw water forward. No tar paper, no metal, just gravity, angles, and paranoia about bulk water finding that inner cavity. This is where the conspiratorial part of Jacob's design shows up. The outer shell was not there to keep him warm. It was there to keep the inner system undisturbed. The logs stopped the wind. The overhangs and drip edges stopped the rain and melting snow. The tight chinking stopped the sideways drafts that would have set up convective loops in the gap. Knowledge that's been buried for over a century hides in that distinction. He wasn't insulating with the outer wall at all. He was protecting the real engine, stone and air working together behind it. And in the next section, when we step inside that shell and watch how he stacked, packed, and sealed that inner wall, you'll see exactly how that seemingly empty space turned into the difference between survival and catastrophe. Now, let's see what Jacob built on the side that actually touched his life. To his neighbors, the outer logs were the cabin. Big, impressive, facing the mountains and the wind. But to Jacob, the real cabin began one step inside that stone and air shell, with a second wall that almost no one ever noticed. This inner wall was the surface his children leaned against, the backdrop for hanging lanterns and rifles, the plane of wood that decided whether the room felt warm or quietly bled heat into the night. He didn't copy the outer wall, he refined it. The inner logs were smaller in diameter, more carefully hewn, planed flatter on the room side, where the outer wall was rough frontier armor. The inner wall was a finished skin, less mass than the stone, more mass than a thin board. Enough thickness to store gentle waves of heat from the stove, but smooth enough that you could press your back against it on a winter evening without catching a splinter. The way he anchored it was the real trick. The inner wall was pinned to its own sill on the floor, its own plate at the ceiling, all riding on that deep stone foundation. But it did not lock solidly into the outer wall. No shared notches, few shared pegs, just occasional lateral ties, sized and spaced so that the two shells stayed standing together without becoming one big thermal bridge. What did this stubborn mountain man understand? That every solid shortcut from inside to outside was a cold highway for his precious heat. Walk the perimeter in your mind. At the corners, he turned the inner logs cleanly, keeping them a disciplined 18 inches from the outer timbers. Around the tiny window openings and the stout door, he framed both walls separately, then trimmed the gap so that the cavity didn't pinch or balloon. That air channel was not an accident. It was a measured dimension. The same width at the north wall as at the south, the same behind the stove as behind the bed, a hidden corridor of trapped air, continuous, quiet, sealed from wild drafts. Inside, when the fire roared, that inner wall was the first to feel it. Radiant heat from the stove soaked into the wood, then into the stone beyond, through that still air. The inner logs warmed, held that warmth, and then, long after the flames fell to coals, they leaked it back into the room as a soft, even glow, instead of a sharp spike that vanished into the cold. In a normal single-wall cabin, the same heat would slam into the logs and shoot straight out into the winter. To Jacob's family, none of that engineering language existed. To them, the inner wall was the cabin. The outer wall and the air gap were ghosts, a hidden thermal machine humming along in silence. Knowledge that's been buried for over a century was nailed into those unseen joints, and in the next part, when we follow a single pulse of heat as it leaves the stove and tries to escape through those layers, you'll see exactly where it gets trapped and where it almost breaks through. But here's the part Jacob never explained to his neighbors, the part hiding in plain sight. That invisible machine wasn't spread evenly through the whole cabin. It was wrapped very deliberately around the human body. Now let's see what Jacob built if you freeze the cabin in a cross-section. From the floorboards up to about 6, maybe 7 feet, you have a thick inner log wall, an 1/8-inch controlled air gap, and the outer wall all marching in a continuous band around the room. Above that, the assembly thins out, lightens, turns more to simple log and roof. Coincidence? In a one-room survival cabin, nothing that takes this much labor is an accident. Think about where the real heat lives in winter, not at the rafters, not under the ridgepole. The human heat radiation zone runs from the floor where your boots sit, up past your chest, to just over your head when you're standing. That's where the stove throws its glow. That's where your body is constantly leaking infrared, like a tiny wood stove on legs. Jacob thickened his defenses exactly around that band. What did this stubborn mountain man understand that his neighbors, with their drafty single walls, never quite put into words? That comfort isn't an average room temperature on a thermometer. It's what your skin sees. If the walls at shoulder height are cold, you feel cold even at 60 degrees Fahrenheit. If they're warm, you feel safe at 52. So he ran that double wall and air cavity unbroken behind the stove, behind the bed, behind the bench where he carved tools and mended boots. The places he sat, slept, and worked the longest ended up backed by the thickest, most controlled assembly. Stand by the stove. Your chest faces dense inner logs that have been soaking up heat all evening. Lie down on the sleeping platform. The wall beside you is part of the same thermal belt, still radiating gently at 3 a.m. when the fire is ash. Pattern interrupt. This was not insulation with air in the way his neighbors mocked around the woodpile. This was targeted insulation around the human. Inside that belt, the inner wall and any stone Jacob tucked near the stove acted like a slow-charge battery. During a hard burn in the evening, that mass absorbed surplus heat instead of letting the air spike and then crash. Once the fire dropped and the cabin air began to cool, the warmed logs and stone quietly reversed the flow, bleeding energy back into the human zone for 6, sometimes 8 hours. Before we reveal the exact technique of how a single burst of heat ricocheted through that belt, notice the pattern. He wasn't designing for abstract R values. He was designing for where his body would be at midnight in January. Knowledge that's been buried for over a century is that this crazy wall wasn't about structure first. It was about comfort patterns. That's the difference between survival and catastrophe when the wind off the mountains finally kills the fire. So when word got around that he was leaving a deliberate hollow in the middle of his cabin walls, the men who'd frozen and survived in those mountains for 20 winters came to have a look. They did not come quietly. First up the trail was Eli Turner, a trapper whose beard had more winters in it than Jacob had years in America. Eli had built, repaired, or helped raise nearly every cabin within a day's ride. His fingers were twisted from frostbite, his reputation from not wasting timber. He walked the line of Jacob's double wall, boots crunching in the frost, and snorted. A castle to freeze in, he said loud enough for the wind to hear. 2 walls and no guts. You're building a barn with a hollow belly. Behind him, Marko Vacek, the sawmill owner from down in the valley, scratched his jaw. Marko knew board feet like other men knew their own children's names. He'd been sawing for ranchers and railroad crews for 15 years. If there was a way to save a plank, Marko had already done it. You're paying for twice the framing, he told Jacob, tapping one of the inner studs with a knuckle. Twice the nailing, more timber, same inside space. All for an empty gap that'll just trap cold air and sweat water. This isn't a cabin. It's a draft with a roof. Now, let's see what Jacob built through their eyes. 2 separate walls of logs and studs, spaced off each other with careful blocks, leaving that stubborn airspace in between. No stone in the middle this time, no heavy thermal belly. Just nothing. To men who believed solid wood was the only thing standing between their bones in the night, it looked like sabotage. What did this stubborn mountain man understand that they didn't? Eli and Marko were not fools. Their cabin stood. Their families had made it through blizzards that snapped wagon tongues and froze creek water solid to the bottom when they said an empty gap would fill with moisture, rot the walls, and let cold slide down like water through a flume. The other neighbors nodded. A self-taught builder named Harris McKee, proud of the dozen single-wall cabins he'd thrown up from Idaho to the Yellowstone, shook his head. Air don't work unless you pack it in tight, he declared. You leave it open like that, it'll just roll. Warm up here, cold down there, turning over all night. You'll be feeding that stove like a locomotive just to break even. Their objections were practical, not theoretical. Double the framing work. More logs dragged out of the timberline. More nails, more time, more chances for something to go wrong. And all to create a cavity they were sure would become a cold lung, inhaling heat from the inner wall and exhaling it straight into the outer logs. Knowledge that's been buried for over a century is that this kind of social pressure could break most men faster than the wind. These weren't armchair critics. They were the accepted wisdom of the valley, walking around in worn boots and wool coats. Jacob listened. He wiped sawdust from his hands. He did not argue. He set another spacer. He lifted another board. The hammer blows answered for him. While his neighbors laughed at wasted timber, he kept cutting, nailing, and keeping that gap exact, trusting something he'd noticed about how heat really moved in a tight cabin when the fire went dead and the winter pressed in. Before we reveal the exact technique that made that empty space work, you need to see what those men had never measured, how air, trapped just right, can turn nothing into the difference between survival and catastrophe. The men watching him work weren't worried about heat first. They were worried about rot. In a Montana winter, cold is obvious. You feel it in your teeth. But moisture is the quiet killer. The moment Jacob mentioned a hidden air gap inside a double wall, every old-timer in that valley had the same reaction. You're building a mold factory inside your cabin, Reinhardt. Weno Bridge and Everbridge. Their fear was simple and very technical at the same time. A dead airspace between log and stone, sealed from sight, meant one thing in their minds: water that could get in but never get out, condensation on the cold side of the cavity. Frost in January, dripping in March. Wet logs that never saw the sun. The perfect slow-motion recipe for rot, mold, and structural failure that would only show itself when the wall finally sagged. And that fear wasn't crazy. When warm, humid indoor air meets a cold surface hidden inside a wall, the temperature can cross the dew point and water appears from nowhere. Tiny droplets, a thin film. Season after season, that film soaks into wood fibers, swells them, breaks down lignin, and invites fungi. You don't need a leak. You just need temperature, humidity, and time. There was a story that made the rounds in the mountains. A miner down near Virginia City had tried a crude double wall 10 years earlier, 2 rough log shells with a gap he filled halfway with bark and straw, then left the rest as a mysterious cavity he bragged would hold the heat like a thermos. The first winter, it felt warm. The second winter, the inside wall began to smell. By the third spring, when they pulled a plank, the inner faces of the outer logs were black and fuzzy, soft enough to push a knife into the hilt. That was the cautionary tale Jacob's neighbors threw at him. We've seen this movie, German. It ends with your cabin collapsing in the mud. They didn't have psychrometric charts. They had a rotted wall and a failed experiment. But Jacob had something they didn't: years of quiet observation. In older cabins, he'd noticed a strange pattern. Tight corners with no air movement went dark and musty, yet certain narrow gaps behind roof purlins, where a thin draft could sneak through, stayed dry and even a touch warmer to the hand. Air, when it could move just a little, seemed to carry moisture away instead of trapping it. Now, let's see what Jacob built in light of that. He wasn't just leaving a random hollow. He was shaping a controlled cavity. The inner stone rose from a deep, cold-resistant foundation. The outer log wall broke the wind. Small, deliberate paths at the top and bottom of that space hinted at venting, not stagnation. This wasn't a sealed jar. It was a lung. So here's the real puzzle. Did he accidentally stumble into a moisture-safe system? Or did this stubborn mountain man understand something about venting and drying that his neighbors and most modern builders still miss? Because when the first real thaw hit that valley, what formed inside those hidden walls would decide whether his bold idea became knowledge that's been buried for over a century or a rotted warning no one dared repeat. So while those hidden cavities quietly decided whether they would rot or breathe, life in the valley went on. And life in the valley meant one thing: people watching. By midsummer, Jacob's cabin didn't look clever. It looked wrong. 2 log walls with a strange, overfed thickness, a shadowed gap between them where any sensible man would have packed moss, straw, anything but air. His neighbors would slow their wagons as they passed, reins slack, eyes narrowed at this double-walled experiment. They didn't keep their opinions to themselves. One man spat tobacco into the dust and said, loud enough for Jacob to hear, "I'll give it till the first real cold. Then you'll see that family in my spare bunk," teeth chattering. Another laughed and started taking bets on how many nights below zero before Jacob's wife begged to move into a normal cabin. This was social science, frontier style, ridicule as quality control. Now, let's see what Jacob built when no one was looking. While the talk circled like crows, he just kept stacking boards. Inner plank wall, outer log wall. Measuring the cavity between them with a scrap of marked lath, checking the gap again and again. Too wide, and air would start to move, turning that space into a tiny wind tunnel. Too tight, and he'd lose the very insulation he was gambling the winter on. What did the stubborn mountain man understand that his neighbors refused to see? He wasn't leaving it empty. He was shaping the cavity like a tool, narrow bays, interrupted paths, every brace, every ledger board placed to break up convective loops before they could steal his heat. While other men bragged about how fast their single-wall cabins went up, Jacob fussed over quarter-inch differences inside a wall no one else thought about. Around him, conventional cabins exploded out of the ground. 1 week. Sills, walls, roof chinked and done. Smoke from fresh stovepipes already smudged the cold blue sky. Jacob's place lagged behind, a slow, deliberate project that looked more like a carpenter's experiment than a home. The pressure to just do it the normal way wasn't abstract. It was right there in every sideways glance, every, there's a reason folks don't build like that. And the risk wasn't academic. If his theory of trapped air failed, he wouldn't just be cold. He'd be the fool who wasted a season and precious timber chasing knowledge that's been buried for over a century. The man who chose physics over tradition and lost. On this frontier, reputation could be the difference between survival and catastrophe. Before we reveal the exact technique he used to keep those cavities dry and that cabin warm, picture the end of that season. First autumn frosts silvering the grass, breath hanging in the morning air. And in the middle of that valley, Jacob's nearly finished double-wall shell, looming thicker and stranger than any other cabin in sight, waiting for the cold to prove him right, or expose him completely. By the time the last chinking was pressed in and the roof shakes were pinned down, Jacob's place didn't look like a cabin. It looked like a fort that had wandered out of a military manual and gotten lost in the Montana mountains. Now, let's see what Jacob built. From a distance, you notice the stance first. Low, squat, heavy. The walls were so thick, the eaves barely seemed to overhang them. Where the neighbors' single-wall cabins sat light on the ground, logs stacked like a hastily made fence, Jacob's structure squatted on its oversized stone foundation like it was bracing for a siege, not a winter. Walk closer, and the oddness sharpened. Window openings were deep tunnels through wood and stone, reveals you could sit inside with your knees pulled up. The sills felt like parapets. The door wasn't just a plank in a hole. It was a short passage, framed by thickness on both sides, telegraphing mass with every step you took toward it. From certain angles, you could lose sight of the actual window glass inside those recesses and see only shadow. That look wasn't an accident. It was the price of the structure he'd chosen. Double log walls, and 1/8-inch cavity filled with stone, and beneath all of it, a foundation dug down to where the soil finally stopped shifting and hit firm gravel and bedrock. While other men scraped a shallow trench, dropped a few flat rocks, and called it good, Jacob kept digging. Wider footprint, deeper base. More stone under the sill logs than some cabins had in their chimneys. His sill logs were brutes, oversized, hand-picked, flattened on top to carry the extra load without twisting. Every additional pound of wall meant more stress at those corners, more leverage for frost heave to grab hold of in January. Neighbors watched him roll those timbers into place and just shook their heads. Who builds a bunker to trap heat? There were trade-offs you could see from the road: fewer windows, smaller panes, while other cabins showed big, bright openings to catch the rare winter sun. Jacob punched in just enough glass to live with and no more. The thermal belt of stone and air had to stay unbroken. Every extra opening was a weak point, a place for heat to leak and cold to pry. That meant a darker interior, especially in December, when the sun skimmed low over the ridge. His neighbors joked that he'd need a lantern at noon. They called it Reinhardt's blockhouse, asked if he was expecting a war rather than a blizzard, and quietly placed bets on how long those heavy walls would last before the snow load shifted something and cracked it all apart. What did this stubborn mountain man understand that they didn't? From the outside, nothing about that cabin whispered efficient or smart. It just looked overbuilt, odd, and a little obsessive. Before we reveal the exact technique that turned those strange walls into a working thermal battery, you need to see how the first true cold tested that fortress shell, and why, that winter, the joke quietly moved to the other side of the valley. That first winter storm hit before Jacob had finished sealing the inner skin of the cabin. For a few days, there was a moment in time when you could actually walk inside the secret of those walls. Now, let's see what Jacob built. Imagine stepping off the rough plank floor and sliding sideways into a hidden hallway that circled the entire cabin. On one side, the outer log wall, dark, massive, cold to the touch. On the other, the rising skeleton of the inner wall. Between them, a wooden corridor barely 18 inches wide, just enough for a man to turn his shoulders and shuffle through in the half-light, the smell of fresh sap and stone dust hanging in the air. It wasn't a clean, open tunnel. Every 3 to 4 feet, cross braces tied the two walls together like ribs in a giant wooden animal. Some bays were filled nearly solid with stone up to 7 feet high. Others, especially near corners and around the stove area, had deliberate gaps, narrow vertical slots where Jacob left mostly air, the stone stepping back just an inch or two from the inner boards. To a neighbor peeking in, it looked chaotic. To Jacob, each cavity had a job. Some sections formed continuous stone from floor to shoulder height, a solid thermal spine. Others were broken into shorter pockets, 6 to 8 inches wide, capped by horizontal planks. Those little pockets trapped still air, reducing convection the way modern builders rely on tight stud bays. What did this stubborn mountain man understand about heat that 2 generations of American frontiersmen had overlooked? Up near the top of the wall, just under the roof plates, he left thin, finger-wide gaps every few bays. Not enough to feel a draft, but enough that if moisture crept into that hidden corridor, a slow, invisible breath of air could carry it out. Down at the bottom, behind the base logs, he carved discrete notches that connected the cavity to the cool, dry stone foundation. No big chimney effect, no roaring convective loop stealing heat, just a controlled, throttled exchange to keep the air dry and the stone from sweating in deep winter. Facing that cavity, he didn't leave rough bark and splinters. The inner surface was planed and tight, smoothed boards turned inward, fewer ledges for dust, fewer traps for damp. In a few key bays near the stove, he even tacked thin, bright metal scraps, flattened tin, shiny side toward the gap, crude reflectors, bouncing radiant heat back into the stone and the room instead of letting it bleed into the outer wall. This was not empty space. It was a carefully bounded volume of air, broken into tuned sections, meant to stay mostly still and dry, hugging 8,000 pounds of stone. Knowledge that's been buried for over a century, hiding in an 18-inch gap. And once Jacob finally closed that inner wall, no one would see this hidden corridor again. Yet the way it behaved on the coldest night of that winter would reveal the difference between survival and catastrophe. The strange part is this: by all rights, that hidden corridor of air should have betrayed him. In a normal cavity, warm air next to the inner wall rises, slides across the top, cools against the outer wall, then drops like a slow-motion waterfall of cold. That loop just keeps spinning, bleeding heat from inside to outside. It turns your wall into a lazy, invisible chimney. And in a Montana winter, an invisible chimney is just a quiet way to freeze. So why didn't Jacob's cabin do that? Why didn't 8,000 pounds of stone, wrapped in air, just pump its warmth straight into the mountainside? Now, let's see what Jacob built when you zoom in, not from the outside, but from the perspective of a single pocket of air. The gap wasn't some giant open shaft. 18 inches sounds big, until you fill most of it with irregular stone and cross ties of wood, leaving crooked, broken-up channels. He added horizontal blocking and ledger pieces to carry the inner wall. Each one sliced those potential convective loops into smaller cells. Small cells mean short racetracks. The air can try to rise, but it hits a ceiling. It can try to fall, but it runs into stone. The loop shrinks, loses energy, and slows down. Instead of one big, roaring conveyor belt of heat loss, you get dozens of tiny, sluggish eddies that barely move. What did the stubborn mountain man understand without equations or CFD simulations? He knew that still air is insulation, but only if you don't give it room to run. Modern building science will tell you the same thing. Still air runs about R1 per inch, but let it form tall, continuous cavities, and those convective loops gut your R value. Then there was the inner wall itself. Those interior logs and boards didn't spike hot and cold every hour. They had their own thermal mass. When the fire roared, the inner surface warmed gradually. When the flames died, it cooled gradually. That softened the temperature gradient across the cavity. Less temperature difference means less engine to drive air currents. You're not slamming hot against freezing. You're easing warm against cool. Pattern interrupt. Here's the twist. The goal was never zero air movement. A little, very slow drift inside that wall did something useful. It shared heat between stones, smoothed out hot and cold patches, and helped keep the cavity above the dew point. That meant fewer hidden cold spots, less condensation, and no secret veins of frost chewing at the logs. Before we reveal the exact technique modern builders use to mimic this, understand the connection. High-performance walls today don't just cram in insulation and hope. They use double-stud walls, service cavities, and vented rain screens to control, not eliminate, air movement. Tiny, deliberate gaps, baffles that break loops, membranes that decide where air can and cannot go. Knowledge that's been buried for over a century shows up again, this time in codebooks and energy models, all echoing the same frontier lesson. Let the air in your walls exist, but never let it run free. That quiet, controlled air inside the walls was about to meet the one thing no builder in the valley could negotiate with: winter. Not the usual Montana winter of hard frosts and squeaking snow. This came early, and it came mean. First week of November, a gray wall rolled over the Bridger Mountains and dropped 4 days of storm on the valley. Snow so wet and heavy it snapped willow poles. Then the temperature fell out from under it. Rivers that normally skimmed over with ice in December locked solid before Thanksgiving. Trappers coming down from the high country talked about mules freezing in their harness overnight, about lines of beaver traps buried under 6 feet of drifted snow. One trader swore he saw a steer dead in the field, nostrils sealed with ice before it hit the ground. Exaggeration? Maybe, but the fear behind it was real. At the post, the elders pulled out brittle ledgers and older memories. They pointed to the winter of '49 to a penciled note that read, "Coldest in living memory." Chickens froze on the roost. Then they shook their heads and said this one felt worse. This wasn't just another season. This was shaping up as a once-in-a-generation test for every cabin, every barn, every wall in that valley. You could see it in the way the neighbors moved. Fast, a little frantic. Men up on ladders, ramming extra moss into log joints. smearing fresh mud chinking that froze almost as it left the trowel. Kids hauling whatever passed for insulation to the gaps. Old blankets, grain sacks, even flattened packing crates nailed over the worst of the windward walls. Windows disappeared behind nailed-up planks and oiled canvas. Firewood piles, which had looked generous in October, suddenly seemed tiny. You could hear axes in the timber from dawn to dark, the sharp ring of steel on frozen grain as families tried to cut one more cord before the next storm hit. Everyone knew what the elders weren't quite saying out loud. This winter might be the difference between survival and catastrophe. And Jacob, the stubborn mountain man with the air cabin, he didn't scramble. He moved slow, methodical, almost annoyingly calm for a man whose neighbors were betting his double-wall experiment would turn into an icebox. He walked his stacked firewood like a quartermaster, counting rows, shifting splits under cover, making sure the driest loads were closest to the cabin door. He checked stove seams with a candle flame, watching for the slightest flicker where hot air might be escaping instead of feeding his stone and air. He packed a little extra clay around the stovepipe collar, then went back to the walls. Now, let's see what Jacob built under pressure. He ran his hands along the inner logs, feeling for drafts, listening for the faint hiss that meant his carefully trapped air might be trying to run free. Where he found a leak, he didn't just smear more mud. He adjusted tiny vents, tightened board covers, tuned the system like a man who understood that air was both his insulation and his enemy. Neighbors watched from their yards, breath steaming, arms full of emergency firewood, trading quiet jokes about the fortress cabin that was mostly air. What did this stubborn mountain man understand that they didn't? The question hung there with the frost. Then the first truly brutal night lined up on the horizon. Forecasts were just stories back then. Ravens flying low, a ring around the moon, trappers muttering about -20 and worse. Families banked their fires, barred their doors, and almost in spite of themselves, kept an eye on Jacob's dark shape against the snow. By dawn, they'd know if his walls of trapped air were genius or a very, very cold joke. Dawn didn't break so much as leak into the Bridger Mountains, a gray smear over a white, wind-carved world. This was thermometer time. This was when the numbers, the frost, and the breath in the air would tell the truth about every cabin on that ridge. Most families had one measuring device, a cheap mercury thermometer tacked near the door. The glass fogged, the scale chipped. They had other gauges too, the line of frost climbing the inside of a window, the ring of ice around a water bucket, the way a wool blanket snapped stiff when you shook it out. Primitive, yes, but brutally honest. In the neighbors' cabins, the first real plunge below -20 hit like a verdict. Men woke with beards frozen to their own collars. Children exhaled little white clouds over their bedrolls. A thin sheet of ice filmed the wash basin. One woman later said her bread dough froze solid before it could rise. The mercury by the door read 38 to 42 degrees inside, and that was after stoves had burned almost nonstop until midnight. This was normal. This was frontier life. But it was also the difference between survival and catastrophe when the winter stretched long. Now, let's see what Jacob built. His cabin had the same cheap thermometer by the door, same brand, same pitted glass. Outside, the air knifed at -22. Inside, after the fire had burned low to coals around 1 in the morning, the needle at dawn still hovered in the mid-50s. The frost on his windows, only a feathery band clinging to the outer edges of the panes. The center glass stayed clear, weeping a little condensation but never feathering white. In the neighbors' single-wall cabins, frost crept across interior log joints like spiderwebs, tracing every gap. You could run a finger along the inside wall and feel crystals. Their stoves, fed last at midnight, left those rooms dropping into the high 30s by dawn, sometimes colder on windy nights. Comfort lasted maybe 90 minutes after the last armload of wood. After that, the cold reclaimed its rent. Jacob's airwall cabin held its warmth for 4, sometimes 5 hours. The family woke without ice on blankets, without that painful moment where you see your breath and hesitate to leave the bed. Water in the bucket skimmed cool, not frozen. A candle flame near the wall burned steady, no sneaky draft tugging it sideways. What did this stubborn mountain man understand that his neighbors, with their sensible solid walls, had missed? No one on that ridge could explain R values or convection loops. They didn't know that still air, trapped in thin layers, resists heat flow far better than a single thick log bleeding warmth straight to the night. They just watched one cabin in the mountains behave differently. Less wood burned, about half a cord where others fed. More heat stayed inside. And with each brutal morning, Jacob's nothing walls of air stopped looking eccentric and started looking like knowledge that's been buried for over a century. Before we reveal the exact technique behind those walls, one question began to gnaw at his neighbors. If empty space could beat their solid timber, what else about their cabins was quietly betraying them? The betrayal showed up first thing in the morning. In the conventional cabins, dawn didn't begin with birds or sunlight. It began with shivering. A gray light over the mountains, a thin crust of ice on the wash basin, and a father waking up already wearing wool trousers, shirt, and socks, under 2 quilts. This was normal. This was frontier life. He'd hold his breath, then throw the covers back. The air hit like a slap. You could see it in the way his shoulders hunched, in the little puff of steam from his mouth as he crossed the plank floor. Boots were stiff with frost. The iron stove was a dead black circle in the center of the cabin, surrounded by air that felt only a few degrees above the world outside. Children knew the ritual. They stayed buried, only noses peeking out, bargaining for just one more minute because the cold actually hurt. No one wanted to be the first to leave the bed. No one wanted to be the one whose bare hand touched that icy latch on the firebox. So the race began. Open the draft, fumble with kindling, pray last night's coals hadn't gone completely out. Until the new flames caught, there was no breakfast, no conversation, just clenched jaws and stamping feet as the cabin slowly remembered what heat felt like. Now, cut to Jacob's air wall cabin on the same winter morning. His fire had gone out hours earlier, yet when he swung his legs over the side of the bed, the floor didn't bite. The air felt tolerable. Not summer warm, but not hostile. He moved in a single shirt, not 3. His wife wrapped a shawl, more out of habit than desperation. The children stepped out of bed without that sharp intake of breath. Here's the pattern interrupt. In the neighbors' minds, a cabin was either blazing hot near the stove or freezing everywhere else. Jacob had something in between, an even, gentle background warmth. What did this stubborn mountain man understand about heat that made shirt sleeves at sunrise possible when everyone else was still shivering in layers? They could sit at the table, away from the stove, and actually eat. No one had to cling to the iron-like shipwreck survivors. Less condensation beaded on the inner wall logs. There weren't little glaciers creeping down the corners. Food stores inside didn't freeze solid by morning, so you didn't wake up to rock-hard potatoes and a block of lard you could barely chip. Clothes told the story too. In the conventional cabins, anything hung up overnight might be as damp as when it went on the peg, sometimes rimmed with frost where breath had hit it. In Jacob's, shirts and mittens actually dried. The air had enough steady warmth to pull moisture out instead of trapping it on every cold surface. That changed the workload. When you're not chained to the stove, feeding it every hour just to keep the cabin above freezing, you win back time. Jacob could let the fire go down, step outside in daylight, and cut wood instead of burning it in panic. He could mend harness, reset a trap line, repair a broken sled runner, while his walls quietly held and released heat. Over one night, the difference was comfort. Over one winter, it was capacity. More energy for hunting instead of huddling. More days spent repairing tools instead of recovering from chill. In a season where the line between thriving and barely hanging on was razor thin, that quiet, invisible cushion of warm air inside his walls wasn't a luxury. It was the difference between survival and catastrophe, and his neighbors were starting to notice. Before we reveal the exact technique Jacob used to tame that air, we need to look closer at what, physically, was happening inside those empty-looking walls. So when that invisible cushion of warm air was quietly doing its job inside Jacob's walls, the mountains were doing something else entirely. They were turning what people thought was a hard winter into a slow-motion crisis. In a normal Montana winter, a family in a single-wall log cabin might plan on 10 to 12 cords of wood from first snow to spring thaw. That's a season of steady cold, some deep snaps, but with breaks where the fire can die down. This winter didn't break. Week after week near minus 20 degrees Fahrenheit, wind scouring the ridges meant those careful estimates blew past their limits. By late January, you could read the story just by looking at the yards. Wood piles that had stood taller than a man in November were now ragged, hollowed-out shells. Neighbors who had calculated, measured, and bragged about their stacks were suddenly doing the same math in their heads and coming up short. How long until we hit dirt? How many nights can we keep the cabin warm if the wind gets worse? This was when the panic cutting began. Men stumbling out at dawn in air that froze the inside of their nostrils, trying to drop green trees with numb hands because the seasoned wood was nearly gone, axes glancing off icy bark, saws binding in frozen grain. Every hour spent in the forest was an hour their cabins cooled. Wives and children huddled closer to a shrinking fire. Now, let's see what Jacob built into his winter plan. His pile was shrinking too. No one escapes a winter like that for free. But while neighbors were burning 2.4, even 2.8 cords a week just to hold on to 40 degrees Fahrenheit indoors, his air wall cabin was sipping closer to half that. Maybe 1.2 cords per week, sometimes less when the wind dropped. Enough that his stack still had a solid, reassuring mass, while others were hitting bare ground. He could pace his cutting, choose the warmer midday hours, dead-standing trees that split clean, instead of rustling green logs in the dark. What did this stubborn mountain man understand that his neighbors did not? That slowing the rate of heat loss through a wall doesn't just feel nicer, it changes your entire schedule, your risk, your odds of seeing spring with fingers and toes intact. In energy terms, it's simple. Every BTU that doesn't leak through a wall is a BTU you don't have to pull out of a log. Standard cabins with leaky single walls were hemorrhaging heat, forcing the stove to pump tens of thousands of BTUs per night just to claw their way to barely warm. Jacob's trapped air cut that leak. Still air, held in controlled cavities, has a real R value. It slows conduction, chokes off convective loops, and keeps radiant heat bouncing around inside instead of bleeding into the cold. That nothing in his wall translated directly into fewer BTUs burned, fewer trees dropped, fewer desperate trips into the forest when the thermometer was trying to crawl off the bottom of the scale. And this is where that old cabin starts to sound uncomfortably modern. Because if a simple air wall could cut Jacob's wood use nearly in half, what does that say about your heating bill, your generator runtime, the size of the solar and battery system you'd need in an off-grid build high in the mountains? Before we reveal the exact technique he used to tame that air, you need to see how those BTUs, those walls, and that empty insulation are the same numbers you're paying for every single winter. So here's the uncomfortable question Jacob's cabin forces you to ask. Did a man in the 1870s, with no fiberglass, no foam, and nothing in his walls but air and stone, come close to beating a modern insulated wall in that brutal Montana winter? On paper, the answer should be no. Modern walls look invincible in a spreadsheet. A basic 2x4 stud wall with fiberglass bats, around R13 in the cavity, maybe R15 once you add sheathing and siding. Step up to a 2x6 with dense packed cellulose and you're in the R19 to R21 range. Add exterior foam sheathing and you can push that effective number into the mid-20s or higher, especially once you cut down on thermal bridging through the studs. Now, let's see what Jacob built. His insulation was still air, tucked between log and stone and more log. Still air is only about R1 per inch. That sounds terrible. 18 inches of open, uncontrolled air would just become a convective highway. Warm air racing up, cold air pouring down. His neighbors were right to laugh at the idea that air could keep a cabin warm. But he didn't build a hollow drum. He built a maze, multiple narrow paths for heat to move through, not one big chimney. The stone core, the inner log faces, the chinking, the way that one ate, each cavity was interrupted by the irregular faces of the rock turned that empty space into a stack of thin, partially sealed air layers. Each layer slowed conduction. Each break choked off convection. The cold outside still pulled, but it had to fight through obstacle after obstacle. Lab tests measure steady-state R value. A wall at one temperature inside, another outside, held for hours until nothing changes. But that's not how a frontier cabin lived. Jacob's fire roared in the evening, died at night, flared again at dawn. Heat came in pulses. The stone drank those pulses, storing energy, then bleeding it back slowly into the cabin for 6 to 8 hours. That time lag meant that when the outside dropped to minus 22 degrees Fahrenheit, the inside surface of that inner wall didn't crash with it. What did the stubborn mountain man understand about heat that his neighbors missed? That in a climate with savage swings and intermittent heating, the timing of heat loss can matter as much as the raw R value. A wall that underperforms in a lab can outperform in a real winter if it delays that loss long enough to carry you through the coldest hours. So could his layered air and stone rival a modern 2x4 wall in that specific climate for that specific lifestyle? The indoor temperatures and wood use say maybe uncomfortably close, and if that's true, then the next question is even more dangerous. What's the rough equivalent R value of Jacob's wall, and what does that number actually mean for you if you tried to copy this in the mountains today? We're about to put a number on it, and it might not be the one you expect. So let's put numbers to this wall of nothing. Now, let's see what Jacob built in terms a modern builder would recognize. Imagine a slice through that cabin wall. Outside, a weathered log shell roughly 6 inches thick on average. Inside, another log withe or board lining adding maybe 2 inches. Between them, instead of fluffy fiberglass, an 1/8-inch cavity where the real game happens. Trapped air weaving around stone, posts, and braces. Not a neat laboratory assembly. A mountain assembly. Wood first. Softwood logs land around R1 to R1, 0.25 per inch. 6 inches of outer wall gives you maybe R6 to R7. The inner lining adds another R2. That's R8 to R9 before you even count the cavity. Still air, if you keep it from churning, is roughly R1 per inch. 18 inches of relatively calm air isn't R18 in practice, but even if convective loops knock that down by half, you're realistically in the R9 range for the gap itself. Add it up and you're looking at an effective center of cavity R value somewhere around R17, maybe R18 on good days. Now compare that to a modern 2x6 stud wall, same overall thickness, stuffed with fiberglass at R19 plus sheathing, and drywall nudging it to R21. On paper, the modern wall wins. No contest, right? But that's the part Jacob's neighbors never understood. They laughed at the empty wall. They saw no bats, no dense fill, just air and stone and a stubborn German with a saw. What did this stubborn mountain man understand that the spreadsheet doesn't show? 2 things: thermal mass and logistics. Before we reveal the exact technique he used to tame convection in that cavity, look at the math that actually mattered in 1876. Hauling manufactured insulation up into the mountains with oxen and snowdrifts? Impossible. Dropping trees on site and prying stone out of the riverbank? Free. His main insulation was air he didn't have to carry, shaped and slowed by materials that were already under his boots. Cost in town and cost at 7,000 feet are different planets. A modern framed R21 wall needs milled lumber, insulation, vapor control layers, fasteners, and tools that can't freeze. Jacob's double wall needed more framing and a lot more stacking, but no fiddly cutting of bats, no careful fitting around outlets, no plastic membranes to tear. For a man with a sharp axe but no truck, that trade was obvious. Labor followed the same logic. The double wall approach demanded time, not finesse. You could teach a teenager to stack and brace those walls in a day. You didn't need a building science degree to avoid gaps in your fiberglass. You just needed to keep the outer wall tight to wind, the inner wall tight to drafts, and the cavity mostly sealed so the air couldn't race. Is this a magic replacement for every modern wall? No. In a city lot with cheap materials and strict codes, you'd be foolish to ignore high R values. But in a remote, off-grid, resource-starved cabin where freight costs more than lumber, a high-mass, high-air wall can be a rational, even high-performance choice, especially when that empty space is working with the stone to smooth out the wild swings between daytime sun and midnight cold. And here's the twist. Jacob's wall didn't just slow heat loss. It changed the timing of when heat moved. In a Montana winter, that timing, those extra 6 to 8 hours of gentle release, was the difference between survival and catastrophe. In the next section, we'll open up that cavity and show exactly how the air and stone cooperated to pull off that trick. That cooperation between air and stone only worked because Jacob refused to give air an easy path. When you give air a highway instead of a maze, that gentle helper turns into a thief. Think of a tall, hollow wall as a glass chimney you can't see. Warm air near the floor heats up, rises, races up the cavity, dumps its heat into the cold outer skin, cools, and falls back down. That loop never stops. It doesn't just leak a little heat, it pumps heat like a fan you forgot you installed inside your wall. Modern builders still fall for this. A metal-clad shed in the mountains with bare framing, steel outside, plywood inside, and a big open gap in between. In winter, that becomes a cold chimney. The steel skin radiates its heat to the night sky, chills, and the air right behind it plunges in temperature. Warm indoor air at the bottom of the cavity rises to replace it, slamming more heat into that icy metal. The taller the wall or roof, the stronger the convective loop. More height, more pumping. Hollow block walls in windy country do the same thing. The blocks look thick and heavy, but those cores, left open from foundation to eave, become vertical racetracks. Wind strips heat off the outer face. Air in the cores rises, cools, drops. The wall feels massive, but the interior surface still reads cold to your hand. You think you built a fortress. You actually built a heat elevator. DIY builders repeat the mistake with well-intentioned double walls. 2 stud walls, a big empty space between, no blocking, no vents it can actually control. It feels clever, it looks thick, the neighbors nod and say, "That cabin will be warm." Outlets and light switches leak cold drafts. One corner of the room is warm, another is 10 degrees lower. The wall, for all its thickness, feels like the side of a metal barrel. Those are the fingerprints of a cold chimney wall, mysterious drafts near electrical boxes, temperature bands you can walk through, and surfaces that feel far colder than their size suggests. The cavity isn't insulating, it's circulating. Now, let's see what Jacob built instead. He chopped that potential chimney into short, segmented cavities. Stone from floor to 7 feet meant the air couldn't rise uninterrupted. Each pocket was small, its convection weak, its heat transfer slow. The outer log wall meant the wind, the inner stone mass soaked and released heat, smoothing out the driving forces that make air race. What did this stubborn mountain man understand that so many later tinkerers forgot? That air is only insulation when it's still. One careless gap, one tall, open chase, and that insulating air turns back into the enemy it was for most frontier builders. Before we reveal the exact technique you can copy without waking a cold chimney inside your own walls, we need to trace how Jacob controlled those gaps in 3 dimensions. Jacob didn't just trap air, he staged it. Inside that double wall, every surface that faced the cavity was quietly deciding what to do with radiant heat. Would it drink in the infrared from the warm stone and bleed it toward the cold? Or would it bounce that energy back into the cabin, one tiny reflection at a time? Radiant heat moves like invisible light. It doesn't care about drafts or conduction. It cares about what it can see. Put a reflective or low emissivity surface facing an air gap, and suddenly that gap isn't just empty space. It becomes a mirror that throws infrared back toward the interior, cutting one more path for heat to escape into the Montana winter. Modern builders buy this in rolls. Foil-faced insulation stapled to studs, radiant barrier sheathing under roof decks, low-E coatings on window glass that reflect long-wave infrared back into the room while still letting visible light through. All of them, every single one, only really work because they face an airspace. Press foil tight against solid wood, and the magic disappears. Give it a gap, and it becomes a shield. Now, let's see what Jacob built with the materials a mountain man could haul, trade, or scavenge in 1876. No polished aluminum. No factory-applied low-E films. But he did have choices. He could plane his interior boards smoother instead of leaving them rough-sawn. He could whitewash or use light-colored pine instead of dark, heavily smoked planks. He could oil the wood so it darkened and slicked, changing how it radiated heat into that hidden cavity. What did this stubborn mountain man understand, even if he never used the word emissivity, that not all surfaces glow with heat the same way? A lighter, smoother board facing the air gap will radiate less energy into that space than a rough, dark, soot-stained plank. It's subtle, but when you're fighting minus 22 degrees Fahrenheit nights in the mountains, subtle can be the difference between survival and catastrophe. Look around his cabin, and you can almost see the improvisation. Maybe a salvaged sheet of tin from a freight crate, nailed shiny side toward the cavity behind the stove corner. Maybe planed interior boards on the warm side, Bark on logs left rough on the outer wall. His neighbors laughed at the double wall. They never noticed the quiet choices about color and texture. Here's the twist. Even without shiny foil, every board facing that air gap was part of a radiant game. Smooth versus rough. Light versus dark. Clean versus smoke blackened. Each choice changed how much heat those surfaces would beam into the cavity and how much would be reflected back toward the stone core and the room. So when you hear air gap, don't picture nothing, picture a stage. On that stage, surface color, texture, and emissivity are actors, all influencing how heat moves through the wall. And Jacob's next move would push that hidden performance even further than his neighbors ever imagined. So when you hear air gap, don't picture nothing, picture a stage. And that stage didn't shut down when the snow melted. It just changed acts. Summer in the Bridger Mountains came hard that first year after the brutal winter. June sun, thin high-altitude air, and cabins that turned into wooden ovens by noon. Standard single-wall cabins soaked up heat all day. By late afternoon, the inside air was thick, unmoving, 85, 90 degrees, and the walls themselves felt hot to the touch. This was normal. This was frontier life. But there was one cabin that refused to play along. Jacob's double-wall cabin, the same one that had stayed warm in the cold, started doing something his neighbors did not expect. On those same days when the mercury outside pushed into the upper 80s, his interior would hover in the low 70s. You'd step in from the blinding sun, and it felt like walking into shade that actually meant it. The inner wall wasn't cool like a cellar, but it wasn't radiating heat like a stove either. It was delayed. What did this stubborn mountain man understand about heat that 2 generations of frontiersmen had ignored in summer? The answer was the same physics, just running in reverse. The outer logs took the sun. They heated slowly. That heat then had to cross the air cavity and the heavy stone core before it could reach the inner wall. Conduction through wood and stone. Convection in that narrow trapped air. Radiation across the gap. Every step cost time. That time lag is everything. Peak sun at 3 in the afternoon didn't become peak interior heat at 3. It might not show up until 8 or 9 at night, right when the mountain air outside finally started to cool. So while neighbors lay sweating through dead-still afternoons, doors propped open and flies everywhere, Jacob's family could sit inside, shutters half closed, resting at a table that wasn't baking from radiant heat. Pattern interrupt. This wasn't only about comfort. It was about food. In a normal cabin, those daily temperature spikes hammered anything stored inside. Butter softened to liquid. Dried meat picked up condensation on hot, humid afternoons and then cooled fast at night, inviting mold. Jacob's thick, delayed response walls kept the interior swaying smaller. Shelves against the inner wall stayed closer to a steady cool. Not a modern refrigerator, but in 1876, shaving 10 degrees off the peak could mean the difference between survival and catastrophe over a long summer. Now, let's see what Jacob built in practical terms. A 4-season machine. In winter, the stone and trapped air slowed heat leaving. In summer, they slowed heat entering. Same wall, same materials, same nothing air that his neighbors mocked as empty space turned into knowledge that's been buried for over a century. Use time, not gadgets, to control temperature. Before we reveal the exact technique you can adapt today, you need to see what happened when the climate pushed this idea even harder. Those wild shoulder seasons when days felt like July and nights snapped back to November. Those shoulder seasons were exactly when the neighbors expected Jacob's air wall to betray him. Warm afternoons, freezing nights, snow one day, rain the next. Perfect conditions, they said, for wet walls, hidden mold, and a cabin that would quietly rot from the inside out. But year after year, the collapse never came. The logs didn't sponge out, the stone didn't sweat and freeze and blow the wall apart. There were no mushroom colonies creeping out from the baseboards because Jacob didn't have baseboards. He had a double log wall with a mysterious, mostly empty cavity, and after several brutal winters and sloppy thaws, that cabin was still standing straight in the mountains. So what did this stubborn mountain man understand that his neighbors missed? He wasn't just trapping heat. He was managing water. In a climate where moisture is every bit as dangerous as cold, that can be the difference between survival and catastrophe. Now, let's see what Jacob built from the outside in. That outer log wall, the one the neighbors mocked as unnecessary, was doing the quiet work of a rain screen. Snow and sleet hit those outer logs first. Most of the bulk water ran down the exterior, dripped off chinking, and never saw the inner wall at all. The cracks between logs weren't tight plastic seams. They were rough, breathable joints that could get wet, shed water, and then dry in the sun and wind. Any rain that did sneak past had a second test: gravity and air. Behind that outer wall, the cavity wasn't packed solid. Water that got through could run down, drip to the stone foundation, or evaporate into the air gap before it ever touched the warm inner wall where condensation would have been lethal. Here's the clever part. Jacob didn't punch big vents that would turn his cabin into a chimney. He likely left small, controlled openings high under the eaves or low near the sill, just enough for moist air in that cavity to drift out. Gentle pressure differences, tiny convection currents, not roaring drafts. Moisture could escape, but the heat stayed mostly trapped. The materials did the rest. Raw wood, limey, mineral-rich chinking. No plastic membranes, no tar paper, nothing that would trap vapor in one layer and force it to condense in another. The whole assembly could dry in multiple directions, outward through the sun-warmed outer logs, inward toward the slightly warmer inner wall, and up or down along that cavity. Modern builders would recognize this instantly. Rain screen cladding, ventilated facades, those deliberate air gaps behind siding that keep structures dry and surprisingly warm. Jacob was running a 19th century version with logs instead of fiber cement, river stone instead of factory insulation, and knowledge that's been buried for over a century. But that raises a harder question. How do you take this kind of moisture-smart, air-driven design and adapt it without accidentally creating a convective heat highway in your own cabin walls? So how do you steal Jacob's idea without building an 1876 museum piece in your backyard? Before we reveal the exact technique for a modern wall, you need the principles. Because what did this stubborn mountain man understand that still applies in a world of codes, inspectors, and foam boards? First, control air movement. Not crush it, not ignore it, tame it. Second, keep a continuous belt of insulation and mass right where your body lives, from about floor level to 7 feet. Third, combine modest mass with trapped air, then give every layer a way to dry when winter ends and the mountains thaw. Now, let's see what Jacob built, translated into plywood and screws instead of hand-hewn logs. Imagine a double-stud wall, one row of studs for the outside sheathing, a second row for the interior finish, offset so wood never lines up directly through the wall. Between them, a thick zone you could partly fill with insulation and partly leave as controlled air. Or picture a standard framed cabin with insulated sheathing outside, then a small interior service cavity, 2 inches deep, where wires and pipes run without punching holes through your main air barrier. That little gap becomes Jacob's quiet air belt, hugging the warm side of the wall. But here's the catch the neighbors in 1876 never had to name. Convective loops. Make an airspace too wide, and it turns into a tiny indoor weather system. Warm air rises on the inside face, cools at the outside face, drops, and suddenly your insulation is a conveyor belt for heat loss. Modern building science says keep vertical air cavities in the 1/2 inch to 1.5 inch range if they're open top and bottom, or up to about 3.5 inches if they're well sealed and broken up with blocking. Anything larger? Add baffles or horizontal blocks every 2 to 3 feet so air can't make a full lap. Those same breaks also help with moisture. They slow vapor, give condensation a chance to dry, and keep that quiet air from turning into a moldy swamp. Knowledge that's been buried for over a century now shows up in code books as vented rain screens and drained cavities. But the physics is the same cabin logic Jacob used. You cannot just copy a frontier wall and hope the inspector is feeling romantic. Modern codes care about fire spread, structural bracing, and minimum R values. That means fire-rated drywall on the inside, proper sheathing on the outside, and real engineering if you're hanging heavy stone or concrete on a framed wall. You check your local code. You talk to an engineer if you're pushing spans or loads. You make sure that clever air gap doesn't become a hidden chimney in a house fire. So where do you practice this without gambling your whole homestead? Small experiments. A test wall on a shed. A tiny cabin you instrument with a couple of cheap temperature and humidity sensors. One bay with a 2-inch service cavity, one with a narrow sealed gap, one with no gap at all. You watch which wall stays warmest at dawn, which one dries after a rain, which one sweats in a cold snap. In a mild valley climate, you might discover that a simple, insulated sheathing plus a 1-inch interior gap is enough. Up high in the mountains, you might find you need more mass and tighter control of air, because the next question is the dangerous one. What happens when you start moving that air gap to the outside, and suddenly your insulation is fighting the sun as well as the cold? So when you drag that air gap outward, let it face the sun and the storm, you stumble into a whole other tribe of wall assemblies. And here's the twist. They look nothing like Jacob's log cabin in the mountains, but they're speaking the same language. Now, let's see what Jacob built in principle. Then jump a century. Modern builders call one cousin the double stud wall. 2 parallel framed walls, usually 2x4s or 2x6s, standing a few inches apart. The outer wall carries the siding and the weather. The inner wall carries the drywall and your warm interior life. Between them, a fat cavity, sometimes a full foot thick. Today, people pack that space with dense insulation, but the core idea is the same separation Jacob used. Inner structure, outer structure, and a controlled zone in between where heat moves slowly instead of crashing straight out into the cold. In a brutal winter, that extra thickness can be the difference between survival and catastrophe. But the real trick isn't just more insulation. It's that the studs themselves don't line up, so heat can't sprint straight through the wood. It has to fight its way across that cavity, through still air and fibers, losing strength with every inch. What did this stubborn mountain man understand about wall layers that modern energy nerds are now refining with spreadsheets and blower doors? Then there's the Mooney wall, a name Jacob never heard but would have understood in a heartbeat. You take a conventional vertical stud wall, then strap horizontal boards across the inside. That simple move does 2 things at once. It creates a deeper cavity you can fill, and it breaks the direct wood-to-wood path from inside to outside. Thermal bridging drops. The wall suddenly behaves thicker than it looks. Your wiring runs in that horizontal layer, your insulation can stay more continuous, and your heat has one more obstacle before it leaks into the winter night. Pattern interrupt. This isn't just a timber thing. Historic brick and stone cities were playing the air gap game, while Jacob's neighbors were still laughing at his double wall. Masonry cavity walls use 2 layers of brick with a narrow airspace between them, sometimes only an inch or 2. That gap let rain drain, let moisture dry, and slowed the march of heat through dense masonry. Sound familiar? Air as a quiet middleman between the storm and the hearth. Push that idea one step further and you land in the modern rain screen. Cladding held off the main wall by furring strips, a deliberate ventilated gap behind it. Cold air slips in at the bottom, warms slightly, rises and exits at the top, carrying moisture with it. In summer sun, that moving air keeps the main wall cooler. In winter, it helps the assembly dry so it can keep performing. Builders sell it as durability, but the side effect is thermal, a more stable, predictable wall. So Jacob doesn't sit alone in history as some eccentric mountain man who overbuilt a cabin. He's standing at the rough, hand-hewn end of a long family line. Double stud walls, Mooney walls, masonry cavities, rain screens, all of them use structure, then space, then structure again to tame heat and cold. All of them rely on air that's guided, not guessed at. And the question now is, what happens when you stop filling that middle zone with stone or insulation at all and let air itself carry more of the load? And let air itself carry more of the load? That sounds like a late-night internet myth. A cabin insulated with nothing. But pause for a second and look at your own plans. Where do you reach, almost on autopilot, for more material? Another layer of foam on that wall. Thicker bats in that roof. Spray every cavity until it's jammed full. How often do you stop and ask, could controlled air do part of this job instead? Because air is not nothing. Still air, trapped in small pockets, runs around R1 per inch. Not impressive by modern code standards on its own, but that's not the point. The point is, what happens when you treat air as a material you can shape, slow, and seal, instead of a nuisance that sneaks through cracks in winter. Now, picture 3 very different projects. A remote cabin, 3 miles up a logging road where every sheet of foam has to be hauled in the back of a pickup, then on a sled. a temporary winter research hut that will stand for 2 seasons and then disappear. A damp, foggy coastal build where you're genuinely nervous about trapping moisture inside a thick, fluffy wall. In all three, air-based strategies suddenly stop looking crazy and start looking efficient. In that mountain cabin, Jacob's double wall and stone core were one answer. But the same logic can extend to controlled cavities, narrow vertical air gaps that are sealed at the top and bottom to kill big convective loops. Reflective faces turned inward to cut radiant losses across those gaps. Assemblies where a modest layer of insulation works together with tuned air spaces instead of trying to do all the heat work alone. What did this stubborn mountain man understand that still applies here? That the wall is a system, structure, surfaces, cavities, each layer changing how heat, air, and moisture move. Modern codes will still demand a certain R value on paper, and they should. Fire officials will still care what happens if a hidden cavity becomes a chimney. Inspectors will still want to see details that don't grow mold in year 3. So there are limits. You can't just wave a hand and say, it's air, trust me. Large, unbroken cavities can supercharge convection and bleed heat. Certain foil layers need spacing to work. Some jurisdictions will flat out reject assemblies that don't match their tables. This is where careful detailing separates interesting idea from difference between survival and catastrophe in a deep winter. Before we reveal the exact technique Jacob used to keep his own air moving slowly and his stone warm, try something. In your head or on a scrap of plywood in the shop, sketch your crazy wall. Maybe it's double stud with a central air plenum. Maybe it's a rain screen gap tuned for your mountains and wind. Then, in the comments, describe it like you're arguing with Jacob's neighbors. How will you control air movement? Where does moisture go? How does heat enter, linger, and leave? Because once you start thinking in assemblies instead of products, air stops being an enemy. It becomes one more material you build with. But air is not magic. In the wrong place, in the wrong cabin, it can betray you faster than Jacob's neighbors lining up to say, "Told you so." So before you start tearing insulation out of your walls, we need a quick reality check. Where does this whole build with air idea actually break? Start with the wettest enemy Jacob never had to fight. Gulf Coast humidity. Picture a cabin in Louisiana summer, 95 degrees Fahrenheit outside, the indoor air conditioned to 72 degrees Fahrenheit, and a big cool air gap inside the wall. That gap becomes a condensation trap. Warm, wet outdoor air sneaks in, hits a cooler surface, and suddenly you're growing mold farms instead of saving heat. In those climates, drying potential is low. Surfaces stay damp. A large, cool cavity isn't a clever thermal tool. It's a slow disaster. Now jump back to the mountains, but push them farther north. Think northern Minnesota, interior Alaska, those brutal plains where winter doesn't flirt with freezing. It lives there. In that world, a pure air gap wall only works if the air is locked down. Tiny leaks matter. A pinhole at the top of the cavity, a crack at the bottom, and you've built a convective elevator that shuttles heat out and cold in all day long. The wind doesn't care about your theory. It will strip that cavity bare if air sealing isn't obsessive. What did this stubborn mountain man understand that helps explain why his design survived? He wasn't chasing a perfect 70 degrees Fahrenheit in every corner. His cabin was small, low, compartmentalized, few windows, tight spaces, one main heat source. Modern expectations are brutal by comparison. You want big glass to the view. Open floor plans, bedrooms at 70 degrees Fahrenheit at midnight and 70 degrees Fahrenheit at dawn. Those demands turn a forgiving, slow-moving thermal system into a precision machine. Any weakness in the wall shows up as drafts, cold corners, and comfort complaints. Now, let's see what Jacob built versus what you are legally allowed to build. In the 1870s, there was no inspector asking for R21 in the walls and a blower door test. Today, dense urban codes and energy standards don't care that you're using knowledge that's been buried for over a century. They want numbers. In many cities, a pure air cavity wall will simply fail the R value requirements on paper, even if it performs decently in practice. Hybrid assemblies, controlled air gaps plus mineral wool, cellulose, or foam to hit both physics and paperwork. Here's the key. Admitting these limits doesn't weaken the idea, it protects it. It keeps you from turning one clever mountain solution into a rigid doctrine. You use air strategically, where climate, codes, and expectations line up, instead of preaching it like frontier religion. Because in the next segment, we're going to push this even harder. What happens when you take Jacob's quiet air trick and slam it into a modern deep energy remodel with almost no margin for error? So let's flip the lens. Jacob already proved this strange air-assisted wall can work in a brutal mountain winter. But what does it look like when you design your own from scratch, on paper, before a single board is cut? First question is not, what insulation should I buy? It's, what are you actually fighting? Write it down. Hottest afternoon, humid coastal fog, or high desert air that cracks your knuckles. Is this a full-time cabin, a seasonal hunting camp, or a just-in-case shelter you might only rush to when the mountains go white and the grid goes dark? That climate and use pattern is the difference between survival and catastrophe if you get the wall wrong. Now, let's see what Jacob built in principle and then twist it for you. You choose your main structure first: studs, logs, or masonry. A simple 2x6 stud wall in a code-built house, a hand-peeled log shell like Jacob's neighbors used, or a heavy stone or brick wall that already carries a lot of weight and thermal mass. Once that backbone is clear, you ask, where can an air cavity live without making your life miserable? Three main options: an interior service cavity inboard of your main wall, where wiring and plumbing run in a shallow, mostly closed airspace; an exterior rain screen, outboard of your sheathing, where siding hangs over a narrow vented gap; or a full double wall, two independent frames with a controllable void between them. Before we reveal the exact technique, you don't need blueprints. You need a pencil sketch and arrows showing where heat, air, and moisture will try to move. Next, you size that cavity. Too thin and the air barely helps. Too wide, and you've built a tiny weather system that steals your heat with convective loops. Still air is around R1 per inch, only when it's actually still. So you might sketch a 1/4-inch rain screen, a 1.5-inch interior cavity, or a 3 to 5-inch controlled gap in a double wall. Then you add blocking, or horizontal baffles, breaking tall cavities into shorter segments so warm air can't just race to the top and dump its energy into the cold. Venting is your next decision. In a wet climate, that exterior cavity probably needs to breathe at top and bottom so moisture can escape. Inside, you may want the opposite, a mostly sealed cavity that slows convection and keeps the warm side truly warm. What did this stubborn mountain man understand about air? That you let it move where it helps dry the wall, and you trap it where you need insulation. Now look at the surfaces facing that cavity. Smooth, light-colored boards or sheathing reflect more radiant heat than rough, dark ones. Add a reflective foil facing an air gap, and suddenly that simple cavity cuts radiant loss dramatically, especially in a hot summer sun. But in a cold, dry winter climate, a humble, breathable wood board may serve you better than a shiny vapor trap. Pattern interrupt. Don't trust the sketch. Build a slice. One stud bay on a pair of sawhorses, a few feet of double wall with an air gap. Put a space heater on one side, a cheap thermometer on the other, and watch what happens over an evening. Where does condensation appear? How fast does the cold side warm up and cool down? That tiny experiment can reveal knowledge that's been buried for over a century under glossy brochures and R-value charts. Then repeat. Redraw. Ask, if wind drives rain at this wall, where does the water go? If the fire dies at midnight, what is still warm at dawn? You're not copying Jacob's cabin. You're stealing his method of thinking. In the next section, we'll push that thinking into a real, modern remodel and see where this air-first idea snaps and where it quietly outperforms walls packed solid with insulation. And once you start thinking that way, you hit a very uncomfortable question. Why does almost every modern conversation about a wall start with a product? Not, how does heat move through this cabin in January? Not, where will the moisture actually go when the cold hits? Instead, it's, are you using foam, fiberglass, mineral wool, closed cell, or open cell? The first move is to reach for a catalog, not a sketch pad. Walk into a home center. The insulation aisle is lit like a jewelry case, shiny bags, branded cans, charts promising R21, R23, R30, as if a single number on a label is the difference between survival and catastrophe. Where on that shelf do you see trapped air carefully controlled by geometry and detailing? You don't, because air doesn't come in a bag. This is where the abstract villain creeps in. There is no single evil foam baron stroking a cat in a tower. There is a system that only makes money when it sells you more material, more thickness, more layers. It does not profit when you learn to use nothing, empty space, still air, thermal mass, so effectively that you buy less. What did this stubborn mountain man understand that clashes with that culture? He understood behavior. He read how heat, cold, and moisture would move through a wall, the way a hunter reads tracks in fresh snow. Jacob's advantage didn't come from a premium product. It came from refusing to let a product make the first decision for him. Before we reveal the exact technique of his double wall, look at the contrast. On one side, glossy marketing that treats a wall like a uniform sponge you just pack tighter. On the other, quiet, unbranded physics, air gap sized so convection can't set up big loops. Stone and wood, arranged so thermal mass sits where it can charge and discharge without getting soaked. Tiny decisions at every joint and seam that never show up in a brochure. Now, let's see what Jacob built in cultural terms. He built a cabin where the most powerful elements of its performance, air, mass, and detailing, had no logo. His neighbors in the mountains could brag about good, solid logs and maybe a new manufactured liner. Jacob could only point to a strange cavity and a heavy stone core and say, "Watch what it does this winter." But this mindset is still on the table for you. You can be the person who asks, "How is heat actually moving here?" before you ask, "Which product is on sale?" But there's a warning hidden in Jacob's success. The lesson is not to throw every modern material into the snowbank in cosplay 1876. Foam, fiberglass, mineral wool, used with intention, can work beautifully with air and mass. A thin, well-placed layer of insulation can protect a thermal battery of stone. A smart membrane can keep those air cavities dry. The danger is not the products themselves. It's letting them replace thinking. In the next section, we'll take that thinking to a real remodel wall, put modern materials on the table, and force them to compete with air and stone on physics, not packaging. To really understand what Jacob was doing, you have to see something you can't see: heat. Not as a number on a thermostat, but as a slow, determined fluid trying to escape your cabin every single winter night. Imagine you're standing in your own living room. Outside, the mountains are locked in snow, and the wind is pushing against the siding. Now, picture heat inside that room as a thick, invisible fog, pressing against every wall, every outlet, every tiny crack in the trim, looking for a way out. Where does it go first? Through the air. By radiation, straight through glass. What did the stubborn mountain man understand that most of his neighbors never bothered to imagine? He traced those invisible currents, not on paper, in his bones. You can do the same, with tools a lot simpler than an engineering degree. Take an infrared thermometer on a cold night and walk your walls. Point it at the center of a wall panel, then at the corner, then at the outlet. Watch the numbers jump. Or use a cheap thermal camera, and suddenly the cabin turns into a topographic map of heat and cold. Blue streaks where framing members suck warmth out, yellow flares where air is leaking, calm, steady greens where the assembly is actually doing its job. No gadgets. Use your hand. Slide it slowly along a wall. Pause at the baseboard, over a window trim, around that old light switch. Your skin is a crude but surprisingly honest sensor. Now, let's see what Jacob built in your mind's eye. Those neighbors with single log walls, their heat map would show bright, desperate orange near the stove. Then a fast fade to cold at the walls and corners. Thermal bridges everywhere. Jacob's double wall, with its stone and controlled air, would look different. Fewer violent streaks, more slow gradients, a thick band of warmth stored in the stone core, and crucially quiet zones where air wasn't racing, just sitting. Here's how to read what you feel or measure. A cold vertical line on an otherwise warm wall. That's a stud, a log check, a thermal bridge, hauling heat straight outdoors. A warm, almost glowing spot on a cold night around a window frame or outlet. That's not comfort, that's a leak, radiant and convective, where your expensive heat is sprinting for the horizon in those odd areas that feel strangely neutral, not warm, not icy, just steady. That can be the signature of effective trapped air or well-coupled mass doing quiet work. Pattern interrupt? The cabin doesn't lie. Over 20 winters, Jacob didn't need equations. He had frost lines on the floor, draft paths across his bedding, corners that never quite warmed. Knowledge that's been buried for over a century was written right there in his breath on the log wall. Before we reveal the exact technique in a modern remodel wall, try this. Map your own home. Where are the suspicious streaks, the dead corners, the surprisingly calm patches in the worst cold or the peak summer heat? Drop them in the comments. The strange warm band behind your couch, the one icy outlet by the north wall, the stone chimney that stays warm till dawn. Together, we can turn a whole community of cabins into laboratories, and that might be the difference between survival and catastrophe in the next hard winter. Over the next few winters, the jokes dried up faster than the firewood piles. Same valley, same mountains, same brutal cold, but the pattern changed. The loud teasing around the airwall cabin faded, replaced by quiet knocks at dusk, men holding their hats in their hands, pretending they'd just been passing by while their breath smoked in the air. They had eyes. They could see. His roof shed snow evenly, while theirs grew thick icy ridges over the cold corners. His chimney burned clean, while theirs belched dark smoke from overworked fires. His woodpile didn't move. Week after week, one neighbor finally muttered the question they were all carrying. How in blazes are you still warm with half the wood? What did this stubborn mountain man understand that 2 generations of log builders in that valley had missed? He didn't preach. He didn't unroll diagrams on the table or lecture about conduction and convection. He just opened the door, let them feel it. The slow, even heat. No scorched faces by the stove and frozen backs by the outer wall. No cold river of air spilling off the logs at their boots. The cabin felt calm. That was the argument. The first imitation was tiny. A neighbor rebuilding his interior paneling on the north side quietly left a 2-inch gap behind the boards. For running wire later, he claimed. There was no wire within 50 miles, but that thin air pocket, trapped and sealed, dulled the bite of the prevailing wind. The next winter, his children stopped sleeping with frost on the blanket edges. Another man, tired of the endless draft where the west wind slammed his cabin, thickened only that one wall. He built a second interface from rough sawn boards, leaving a hand-whipped cavity, then stuffed just the bottom foot with dry bark to slow the convective loop. Crude, uneven. It still worked. The howl at that wall turned into a murmur. A third neighbor experimented where it felt safe to be wrong, on a tool shed. He framed a double wall, left a wide air gap, and watched. That shed, with no constant fire, held above freezing on nights when his main cabin water bucket skinned over with ice. Knowledge that's been buried for over a century often comes back in these sideways, embarrassed experiments. Before we reveal the exact technique in modern terms, look at the social physics here. Nobody wrote a manual. Nobody drew a section detail. Yet within a decade, the normal cabin in that valley quietly thickened. A second inner skin here, a narrow air slit behind a bunk there, better mass near the stove, not just random stone underfoot. The walls people built began to assume that air could be part of the insulation, not just empty space. Now, let's see what Jacob built in that Montana valley as a mirror to what's happening today in online forums and backcountry videos. One stubborn experiment, posted or built in the middle of nowhere, gets noticed. A service cavity behind drywall, a double stud wall with a deliberate air gap, a tiny off-grid cabin with a weirdly warm corner. You watch, you copy a piece, you tweak it. The frontier had word of mouth around a stove. You have a comment section and a signal bar. The process is the same. Quiet adoption. Incremental change. A new normal that nobody officially declares. But here's the twist almost nobody talks about. When you start using air as your main insulation, the line between a warm, forgiving wall and a cold, dangerous one is razor thin. And that's where we're headed next. Because if you strip this whole story down to one lesson, one thing Jacob's cabin is still shouting across the mountains and across the years, it's this. Air is not the enemy. Uncontrolled air is. Controlled air, shaped and pinned in place, is one of the most powerful, cheap, and overlooked insulation tools you will ever touch. Now, let's see what Jacob built in principle, not in log sizes and nail counts, but in physics. He didn't invent magic stone. He didn't find a secret species of warm log. He respected how heat actually moves, by conduction through solids, by convection in air, and by radiation across empty space. Then he laid out his walls so each of those pathways had to fight for every BTU it stole. Stone in the middle for mass, logs outside to shield it from the wind, tight chinking to kill the drafts, and in between, a controlled, narrow space where air could move just enough to wash heat into the stone, but not enough to set up those big convective loops that strip a cabin bare on a January night. What did this stubborn mountain man understand that his neighbors, piling on more logs and more mud, never quite saw? That nothing is only nothing if you refuse to shape it. This is the part modern builders often miss. We copy our values. We copy wall thicknesses. We copy product names from brochures. Jacob copied the sky in February and the creek in November. He watched where the frost formed on the inside of his neighbor's walls. He felt which side of a stone stayed warm longest after sunset. His success did not come from a product aisle. It came from treating every wall, floor, and roof as a system he could tune, not a recipe handed down by tradition or marketing. That's the broader mindset his cabin is begging you to steal. When you look at your own house, your own plans, don't just ask, what should I fill this with? Ask, where can I use nothing on purpose? A tiny vented gap behind your siding to let moisture out instead of rotting sheathing. A sealed airspace behind a radiant barrier in a roof, turning a thin foil layer into a serious shield against summer heat. A double stud interior partition with a dead air cavity that keeps a bedroom warm while the hallway cools. Before we reveal the exact technique that makes air go from liability to armor, Jacob's walls are already handing you the headline, Design with Physics, not with fear. His cabin is proof that knowledge that's been buried for over a century can still mark the difference between survival and catastrophe in a hard winter, or between a house that quietly bleeds money and one that stays warm long after the fire dies. And if you think using nothing as insulation sounds risky, wait until you see how precise you have to be to keep that nothing from turning on you. So here's where this stops being a frontier legend and starts being your project. You've seen how a mountain cabin with nothing in the wall can still stay warm when the mountains go white and the wind goes sharp. Now it's your turn to test whether a controlled pocket of air can work for you or betray you. Before we reveal the exact technique we're going to build on camera, sketch your own. Grab a scrap of paper, open SketchUp, or walk out into the backyard with a few boards and a handful of screws. Draw or mock up a tiny test wall, one side facing the cold, one side facing the heat, and in between, a deliberate air cavity. Not a random gap, a designed void. Ask yourself, how big is that cavity? 2 inches? 6? A full foot like Jacob's neighbors would have sworn was madness? The research on still air says small, sealed pockets fight conduction and convection. Bigger gaps can turn into little weather systems, with warm air racing upward and cold air sliding down. What did this stubborn mountain man understand about controlling movement that most people still ignore when they frame a cabin wall? On your sketch, mark where you'd block that air. Horizontal baffles every couple of feet. Vertical breaks to stop those convective loops. Then think about venting. Do you keep that cavity completely sealed, or do you give it a tiny controlled way to dry if moisture sneaks in during a wet winter storm? Surface choices matter too. One side rough wood. One side may be a light reflective layer facing the air to cut radiant heat loss. You're not copying Jacob's stone wall blindly. You're applying the principle. Manage conduction, convection, and radiation with geometry, not just with bags of insulation from the store. Drop your sketch ideas and questions in the comments. Show us your weird double stud cabin wall, your backyard test box, your off-grid nothing wall experiment. If you've already built something like this, tell us what happened the first time the temperature dropped below freezing. Because we're not leaving this at theory. In a follow-up video, we're going to build 2 mini walls side by side. One standard insulated wall, one air gap wall, same size, same exposure. We'll wire in thermometers, maybe even bring out the thermal camera, and watch in real time which one bleeds heat when the cold hits. If you want to see that test, and more deep dives into crazy historical building ideas that actually worked, subscribe and turn on notifications so YouTube doesn't bury this knowledge that's been buried for over a century all over again. And share this with anyone planning a cabin, tiny house, or off-grid place up in the mountains. It might save them from hauling half a ton of unnecessary material up a ridge, and it might mark the difference between survival and catastrophe in their first hard winter. Now, let's see what Jacob built compared to what you dare to build today. Now, let's see what Jacob built compared to what you dare to build today, and why it matters far beyond one lonely cabin in the mountains. Picture that winter storm again. Wind at 30 miles an hour, snow blowing sideways, the thermometer sinking toward numbers that make your teeth hurt just looking at them. Out there, the world is loud, violent, and indifferent. Inside, a small, quiet room, a lamp, a stove, and those empty walls doing silent work between you and the cold. That's not just a frontier scene. That's a design brief for the world you live in now. Rising energy costs, rolling blackouts, grids pushed to the edge by heat waves and polar outbreaks. This is our new normal. The question isn't how big can the furnace be, it's how long can this cabin stay warm when the fuel runs out? What did this stubborn mountain man understand about heat and air that entire modern subdivisions still ignore? He understood that if you control air, you control heat, not with gadgets, with geometry, with walls that turn wild convection into slow, trapped stillness. Today, when you hear about R values and spray foam and triple pane glass, it's easy to think resilience is something you buy in a box. But the core idea, managing conduction, convection, and radiation with simple layers and controlled gaps, is knowledge that's been buried for over a century in favor of whatever's on the shelf at the home center. And knowledge like that is a kind of independence no one can sell you and no one can take away. If you understand why a sealed air cavity resists heat flow, why a tight inner wall and a wind-stopping outer shell can keep a space livable at 20 degrees Fahrenheit with limited fuel, you're already ahead of the game the next time the power goes out or the propane truck can't make it up your road. So when you walk past a wall tomorrow, your house, your office, a store, you won't just see drywall and studs, you'll see a battlefield. Heat trying to escape, cold trying to force its way in, air gaps acting as traitors or defenders depending on how they're built. You'll remember Jacob's neighbors laughing at empty walls, and you'll know exactly who was doing the real math that winter. Thank you for staying through this long, detailed story through stone and logs and invisible currents of air. Before we reveal the exact technique in another project, you already carry the part that matters most, the mental model, the sense that design, not just fuel, marks the difference between survival and catastrophe. So we'll close on a quiet note. The camera pulls back. The door of that mountain cabin swings shut. The latch drops. Outside, the wind howls and claws at the logs. Inside, the air is still. The heat lingers. And the walls the experts once mocked hold their line. Now you know the secret. Let the storm do what it wants.